Welcome to Titrations and pH curves. So, we've already talked about acids and bases and pH and how to calculate pH for a strong acid and a weak acid, as well as strong bases and weak bases. So, in an acid-base titration, we have a solution of base of known concentration is being added to an acid of unknown concentration, or an acid of known concentration is added to a base of unknown concentration. Essentially, what we're trying to do here is figure out the concentration of the acid or the base. So we have some flask generally, and into that flask we're putting a solution containing either the base or the acid, the other one, of known concentration. And based on the volume of the known concentration we've added, we can figure out the concentration of the known volume of the other one. So, we generally use either an acid-base indicator or a pH meter in order to signal our equivalence point. Know that the equivalence point here is the point at which stoichiometrically equivalent quantities of acid and base have been added. So we should have a neutral solution then if we have strong acid plus a strong base. So, a plot of pH as a function of volume during a titration is what we call a pH titration curve. So we have the pH plotted over here and the volume of our base added in this case. So we start out with an acid in our flask, so the pH is less than 7. And then as we add the base, the pH slowly rises, and at some point we get this sharp jump here, and then the pH begins to level off again. It still continues to climb as we add more base. And the midpoint there is what we call the inflection point. The inflection point is the equivalence point. And the whole technique is all about figuring out where exactly that equivalence point is. So let's consider a titration of adding a strong base, for example, sodium hydroxide, to a solution of a strong acid, for example, hydrochloric acid. So we can divide our titration curve into 4 different regions. The initial pH before we've added any base, between the initial pH and our equivalence point, at the equivalence point, and after the equivalence point. So we have 2 points, basically these 2 points, where it's just a single point for each one of them. And then these 2 are ranges where we have multiple volumes that we might be looking at. So let's look at the initial pH before any base is added. So we're looking at just this point right there. So the pH is given by the strong acid solution, and this means that our pH has to be less than 7. We've got an acid, so we know the pH is less than 7. Between our initial pH and the equivalence point, remember the initial point pH is there, and the equivalence point is here. So in between those 2 points, so after we've started adding at least a little bit of our base, and before we've added so much that we have stoichiometrically equivalent quantities, this is the region that we're talking about. So when the base is added before the equivalence point, then the pH is given by the amount of strong acid in excess. So whatever however much of our acid we have remaining, right? We've reacted away some of our acid, but not all of it. Okay? And this means that we still have an acid around. It's a strong acid, which means the pH still has to be less than 7. So at the equivalence point, then the amount of base added is stoichiometrically equivalent to the amount of acid originally present. And this means then the cation of a strong base and the anion of a strong acid is what we have left. And these do not undergo hydrolysis, which means they don't affect the pH. If they don't affect the pH, then essentially we have a solution that would act the same pH-wise at least as if we just had pure water, and that means the pH is exactly 7.0. And then after the equivalence point, now the pH is determined by the excess base in the solution. Right? We've reacted away all the acid, the pH is 7. At the equivalence point, once we start adding some more base, or we continue adding more base, the pH is going to climb as if we were just adding base to a solution of pure water. And this means that then the pH has to be greater than 7 because we've got an excess of base around. So, how do we know when we've reached the equivalence point? Well, at the equivalence point, the pH is 7 if we have a strong acid and a strong base. If one of them is weak, then this is not true. But if we're using a strong acid and a strong base, then we can use an indicator that changes pH, that changes near pH of 7. So, phenolphthalein changes color between a pH of 8.3 and 10.0. Below pH of 8.3, phenolphthalein is colorless, and above pH of 10, phenolphthalein is pink. So at the equivalence point then, the solution should be just very slightly pink. If we continue going past that, the solution will get darker and darker pink. So the end point is not the same thing as the equivalence point. Ideally it is, but it's not always in reality. So the end point is the point where the indicator changes color. The difference between our equivalence point and our end point is what we call the titration error. So the titration curve of a titration of a strong base with a strong acid is similar then to the titration curve of a strong acid with a strong base. So if we have a strong, if we are titrating a strong base with a strong acid, that means we're adding the acid. Whatever we're titrating with is what we're adding. What we're titrating is what we started with. So here we're starting with a base, we're titrating with a strong acid, which means as we add the acid, the pH needs to be going down. So we're going to start out with a high pH, and it'll go to a low pH. If we have the titration of a strong acid, that means we're starting out with an acid, it's starting out with a low pH, and we're titrating with a strong base, which means the pH is going to go up. Okay? So the images that I've shown you have been the titration of a strong acid with a strong base. So, in this case of titrating a strong base with a strong acid, the base at the start is in excess, so the pH is less than 7. Greater than 7. At the equivalence point, the pH is equal to 7, and past the equivalence point, the pH is less than 7 because now we have excess acid around. Okay, so now we're going to look at a weak acid, strong base titration. So here we have a weak acid that we're titrating with a strong base. So let's look at the titration of acetic acid with sodium hydroxide. Again, we have a weak acid being titrated with a strong base. So in this case, again, we can divide our titration into 4 regions before we add in any base, between the initial pH and the equivalence point, at the equivalence point, and then after the equivalence point. So before we have any base added, then the solution contains just our weak acid, just the acetic acid, and the pH is given by our equilibrium calculation for the acid. So Ka is equal to the concentration of hydrogen ion times the acetate ion concentration divided by the acetic acid concentration. Between the initial pH and the equivalence point, so after we've added a little bit of our base, our strong base, but not enough to get to the equivalence point. Now, as we add strong base, it consumes some stoichiometric quantity of our weak acid. So we have our acetic acid plus hydroxide gives us acetate and water. The water is not pH active. But now we have a mixture of however much acetic acid we have left, unreacted, and our acetate. So there's still some excess of acetic acid compared to our hydroxide ion, and which means we have an acid, we have its conjugate base, we have a buffer. So that means that we can use the buffer calculation, the Henderson-Hasselbalch equation, to find the pH of our solution. So first we have to find the amount of acetate produced, and then the acetic acid, that's the amount of acetic acid consumed. And then we can calculate the pH using the equilibrium conditions, which means using the Henderson-Hasselbalch equation. So at the equivalence point, this is our third region that we're talking about. So at this point now, all of the acetic acid has been consumed, and all of our sodium hydroxide has been consumed. We don't have any excess sodium hydroxide yet. So what do we have? We've reacted away all of our acetic acid. We formed acetate. So we have acetate ion around. We have sodium ion around. And we have water. And that's it. The sodium ion and the water are not pH active, but the acetate ion is. Remember, the acetate ion is a conjugate base of a weak acid. That means it is also a weak base. So this means that the pH then depends on the acetate concentration. Acetate is our conjugate base of a weak acid, so acetate has to be a weak base. If we have a weak base around it, the pH has to be over 7.0. So remember, this is at the equivalence point. So we have a weak base left after we titrate our weak acid with a strong base, and that means that the pH is not equal to 7 as it was when we had a strong acid, strong base titration. And then last, we have the region after the equivalence point. So this point, then the pH is given by the concentration of the excess strong base. So we start out with, at the equivalence point, we've got our acetate ion, so we've got our weak base solution, and now we add some strong base to it. We can basically ignore the weak base, and we just need to look at the concentration of the strong base, the excess hydroxide ion that's around. So the titration curve for a weak acid, strong base titration looks significantly different than that for a strong acid, strong base titration. We have some cases like this. The strong acid, strong base titration is this black curve. Note that the pH doesn't change much, and this is because we have a lot of hydrogen ion around, because we've got a strong acid. So the pH isn't changing much, and now at this point we've started to react. We've reacted away almost all of the strong acid. There's not much hydrogen ion left, but every time we react a hydrogen ion, we're not making any more, because all of our strong acid has already dissociated. It all dissociated over there. And that means that now, as we add the base, we go up. And then at the equivalence point, we have, for the black curve, the equivalence point is at that point there, at a pH of 7. And then past that, well, then we just have our neutral solution that we're adding base to. But, so that was for the strong acid, strong base titration. That's that black curve. The blue curve is for the weak acid, strong base titration. So in this case now, we start out with a weak acid. We started out with originally the same concentrations. The pH is going to be higher because a weak acid is going to have a higher pH than a strong acid at the same concentration. So you note here that the blue curve goes up very quickly initially, and then it levels out more. And all of this region in here is the buffering region, because at this point, when we initially start, we have none of the conjugate base of our weak acid, which means we don't have a buffer. But once we start to add some base, now we've created a buffer, because now we have some of the conjugate base of our weak acid. So we have an acid and its conjugate base, we have a buffer. So in this region we've got a buffer, and the pH isn't changing much, because when we add some of our strong base, some of that hydrogen ion that's reacting away is getting replaced by dissociation of our weak acid. And this means that the pH isn't changing as much. And so you might say, well, it's still changing more than that black curve is. That's true, except that you can't be comparing the volumes here. You need to be comparing the pH. At a pH of, say, 4, is the blue curve changing less, or is the black curve changing less? The slope on the black curve is far, far higher than the slope on the blue curve at pH of 4. And this is because the blue curve is acting like a buffer. The black curve is not buffered. So, then when we get over here, we've reacted away almost all of the weak acid, and then as we start to add our base, or as we continue adding our base, we've essentially used up almost all of the buffering capacity of our weak acid solution, our buffer here, and then the pH starts to change rather quickly again, because now we have very little of our weak acid left, and the addition of just a small amount of base is enough to change the pH significantly. And then we get to our equivalence point. And again, note that our equivalence point in this case is around a pH of 9. And then after that, the two curves look exactly the same, because after the equivalence point, we've already reacted away all of the acid. And the only thing we have left in the black curve, we have a neutral solution at the equivalence point that we're adding base to. We're adding strong base. On the blue curve, we have a weak base that we're adding strong base to. If we add a strong base to a weak base, the weak base is basically negligible. So, both of the curves look exactly the same after the equivalence point because we're just adding a strong base to our solution. Let's go through this one more time. So, for the weak acid strong base titration, the initial pH is higher and the initial slope of pH as the base is added is significantly steeper until we get into the buffering region. Right? So then the pH slope levels off as the buffer conditions arise, and then near the equivalence point the pH change is less dramatic. Right? We're not changing the pH by nearly as much for the weak acid titration as for the strong acid titration. Again, the equivalence point is higher because at the equivalence point for the weak acid titration, we have a weak base left over. And that means the pH needs to be higher than 7. So the shape of the two curves after the equivalence point is then the same up there. So that was for a monoprotic acid. But in polyprotic acids, then the ionizable protons can dissociate in a series of steps, which means we won't have a curve that looks just like an S. We'll have multiple equivalence points. So our polyprotic acid titrations will have a series then of equivalence points. If we have a diprotic acid, we'll have 2 equivalence points. If we have a triprotic acid, we'll have 3 equivalence points, and so on. So let's look at an example of the phosphate system. So the titration of phosphoric acid, which is H3PO4, with sodium hydroxide, NaOH. So we've got H3PO4. If we pull off a proton, we get H2PO4. We can pull off another proton to give us HPO4 2-. We can pull off another proton to give us our phosphate ion. And you note that each one of these then is labeled with pKa, and this is pKa1 for the first proton being removed. That one has a pKa value of 2.15. The second proton being removed, pKa2, has a value of 7.20, and the third one has a pKa3 of 12.35. So this is what the graph will look like. We've got pH as a function of titrant volume. So as we add our base and we're removing our protons, you can see we start out there with our phosphoric acid. We get to our first equivalence point here, and then we get to our second equivalence point there, and our third equivalence point is up here. Note that that one is rather difficult for us to see, but these two are easier for us to see. Each of these other points here are the midway points between the initial 0 volume of base added and our first equivalence point. That's that point there. At that point, then the pH is equal to pKa1. This is the midpoint between the first equivalence point and the second equivalence point. At that point, the pH is equal to pKa2. This one is the midpoint between the second equivalence point and the third, and that's the pH at which, or that's the volume at which the pH is equal to pKa3. So that was titrations and pH curves.